Welcome, friends. I'm glad you're here. Today we'll journey into the world of earthquakes and the shifting dynamics of fault systems, how immense forces reshape the land and send tremors through our planet. If this gentle exploration sparks your curiosity, please like, subscribe, or share. Thank you. In the deep stillness of geological time, the continents drift upon a surface that is never at rest. Beneath oceans and mountain chains alike, the lithosphere lies divided into immense slabs, each hundreds to thousands of kilometers across, sliding imperceptibly over the softer asthenosphere below. These tectonic plates move only a few centimeters each year, yet over millions of years they carry whole continents into collision, separation, and transformation. The motion is constant but invisible to the human eye, driven by heat deep within the mantle. Convection currents slowly shift mass, carrying the rigid plates as if they were rafts upon a slow, viscous tide. The scale of this movement defies ordinary perception, for a year's travel of a continent might be no wider than a human fingernail, and yet this is the force that assembles and dismantles supercontinents. One quiet irony is that mountains which seem eternal and fixed are only temporary consequences of this restlessness. Another is that the ocean basins, which appear vast and unchanging, are younger than the most ancient rocks on land. And still another is that even while the continents drift apart, microscopic grains of sediment silently bridge them across ocean floors. The driving mechanism remains partly a mystery. While mantle convection, slab pull, and ridge push are widely accepted contributors, the exact balance of forces is still not fully resolved. At mid-ocean ridges, molten rock rises to form new crust, pushing plates outward, while at trenches, old crust sinks into the mantle, pulled downward by its own weight. In between, on the continents, invisible boundaries creep under fields, forests, and cities, marking the edges of plates that rarely announce themselves until they slip. This slow migration is both a process of destruction and creation. As crust is consumed in one place, it is born anew in another. The arrangement of continents we know today is only a transient pattern in an endless sequence of configurations. Millions of years ago, the landmasses were joined as a single body. Millions of years from now, they will converge in new alignments, closing oceans and raising fresh mountain chains. The continents do not travel as solid, undisturbed blocks, but as fractured mosaics, each carrying within it smaller faults and zones of weakness that speak of past collisions and separations. In certain places their drift tears open rift valleys, where the land sags and stretches in long linear depressions. In others, the grinding together of their edges builds ranges of folded and faulted rock. Beneath these features, the boundary zones extend deep into the crust and upper mantle, where heat pressure and mineral transformations continually alter the physical character of the rocks. The surface expression of plate motion is subtle but cumulative. An offset river here, a warped coastline there, a chain of volcanic islands, marking the track of a plate over a mantle hotspot. These small signatures hint at immense forces operating far below. Even as these plates move independently, they are coupled in a global system where the motion of one inevitably affects the rest. The slow collision of the Indian plate into the Eurasian plate lifts the Himalayas ever higher. The widening of the Atlantic pushes North America and Eurasia apart, influencing stresses in distant regions. Seismic networks now record these motions with precision, using satellite positioning systems to detect movements as small as a few millimeters per year. The measurements confirm what geological reasoning long suggested, that the crust of the Earth is restless on a planetary scale, and that this restlessness is not random but part of a continuous coherent pattern. Yet the origin of this great mobility is ancient and elusive. It depends on the retention of heat within the planet since its formation on the decay of radioactive elements deep in the mantle and perhaps on water itself, which weakens the minerals of the lithosphere and allows them to bend and break over geological spans of time. The continents, in their unhurried motion, also carry with them the sediments of eroded mountains, the fossil remains of vanished seas, and the scars of earlier tectonic episodes. They record in their rocks the stories of oceans that opened and closed, of volcanic arcs that shifted position, and of fault lines that once marked the edges of long-vanished plates. The slow drift is impartial and indifferent. It erases as much as it preserves. A quiet irony lies in the fact that the very movement that destroys certain geological features is also what allows them to form in the first place. Another lies in the uneven pace of this process, for while the human mind measures time in days and years, the plates advance in epochs and eras. And yet another is that these vast slow processes are detected in part by the smallest of signals, the tremor of a sensor, the change of a fraction of a degree in a satellite's position. In the present moment, continents rest in their current positions, yet their journeys continue. Africa drifts slowly northward toward Europe. Australia moves toward Southeast Asia. The Americas glide westward over the Pacific's shrinking floor. In deep trenches, slabs descend into the mantle, melting and fueling volcanic arcs. Along ridges, molten rock wells up to replace them. The cycle is perpetual but not symmetrical. Some plates grow in size, others diminish. Some boundaries are lively with earthquakes, others are almost silent for centuries. The forces at work do not pause, though they may appear dormant from the perspective of a single lifetime. Somewhere beneath the quiet surface, stress builds along a locked fault. The strain will one day be released not in the slow drift of the plates, but in the sudden rupture of an earthquake. In that way, the drifting continents are not merely the stage for seismic events. They are the actors themselves, their gradual motion setting the conditions for the abrupt transformative moments when the stored energy of their collisions and separations comes suddenly to light. The surface of the earth seen in this way is not fixed, but in constant silent motion, a mosaic of moving parts whose interactions shape the world we inhabit without ever needing to rush. Deep within the crust, far beneath the surfaces where cities rise and rivers wind, strain accumulates in silence. Rocks, though solid, are not entirely rigid. Under the persistent push and pull of tectonic forces, they bend and deform ever so slightly, storing energy in their mineral bonds. This invisible weight of strain builds slowly year after year without a sound, without a visible mark upon the land. The source is unrelenting, the drift of plates, the creeping pressure at subduction zones, the steady resistance along locked faults. Each grain of strain is too small to sense, but together they form a vast unseen reservoir of potential motion. A quiet irony is that the stronger the fault's resistance, the greater the eventual rupture. Another is that the longest intervals without shaking often precede the most powerful events. And another still is that the ground beneath the calmest landscapes may be under the most intense compression. The mechanics of strain accumulation are well understood in principle, as tectonic forces act rocks in the brittle, upper crust resist movement until their strength is exceeded, at which point they fracture or slip along existing weaknesses. This process is captured in the elastic rebound theory, where the crust behaves like a bent branch that suddenly snaps back into a straighter form, releasing stored energy as seismic waves. Yet the precise thresholds remain elusive. No instrument can yet tell exactly when the rock's breaking point has been reached. This is one of seismology's enduring mysteries. Faults give small hints, tiny tremors, subtle changes in stress, but they rarely announce their timing with clarity. While geophysicists map strain using networks of GPS stations and strain meters, translating this data into prediction remains beyond reach. Strain does not build evenly. It clusters in some places, fades in others, shifting over time as smaller earthquakes redistribute stress, or as deep, slow, slippy vents relieve it without shaking. The scale of these processes invites analogies that shrink the unimaginable to the familiar. The crust as a locked door whose hinges creak almost imperceptibly, until one day the door eases open with a sudden lurch, or as a bow pulled steadily backward until the string can no longer bear the tension. Yet such images, while helpful, barely touch the complexity hidden in the rocks. The accumulation of strain is not a smooth and steady winding of a clock. It is an uneven gathering interrupted by partial releases by changes in temperature, pressure, and pore water content. In some regions, strain builds steadily for centuries before failing. In others, it appears to rise and fall in decades-long pulses. Beneath the Himalayas, the locked thrust faults hold back the slow northward movement of India into Eurasia, storing energy that will eventually be released in a series of powerful earthquakes. Along California's San Andreas Fault strain builds at a measurable rate of several centimeters per year, even in stretches that have not broken for more than a century. The irony is that while we can measure this build-up with exquisite precision, the translation of strain into rupture remains unpredictable. The crust may yield tomorrow or hold for generations. This uncertainty lies not in ignorance of the physics, but in the chaotic nature of fracture itself, where small variations in rock strength, fault geometry, and fluid pressure can tip the balance unexpectedly. Strain is also not merely a surface phenomenon. It extends downward through the brittle crust to depths of 10, 20, even 30 kilometers, where high pressures keep rocks from fracturing easily, but do not eliminate the forces entirely. At greater depths in the ductile lower crust and upper mantle, the rocks flow rather than break, redistributing stress in ways that may either hasten or delay the next rupture above. The stored energy waits in perfect stillness, needing only the smallest trigger, the slip of a neighboring fault, the slow drift of stress from a deep earthquake to tip it into motion. The passage of time alone does not guarantee release. Some faults remain locked far longer than their calculated recurrence intervals, defying expectations. In this way, strain accumulation is both a process and a puzzle, a steady gathering of potential that resists simple clocks and tidy forecasts. The land above gives no obvious sign. Forests grow, rivers meander, cities expand, all unaware that beneath their foundations the crust is holding its breath. It is an irony of scale that human lives, with all their urgency and change, unfold within the quiet patience of strain, building toward an event that may be centuries away. And yet when the moment arrives, the release will happen in seconds, transforming decades of silent accumulation into a burst of seismic energy that can shake an entire region. Between those two states, locked and ruptured, lies the long imperceptible preparation that defines the earthquake cycle. Strain once released will begin to build again, as the plates never stop moving, never stop pressing against one another. The cycle is not a perfect circle, but a rhythm that changes its pace, influenced by the geometry of the fault, the composition of the rock, and the history of past ruptures. In some places, the same segment of fault will break repeatedly over centuries. In others, the location of rupture will shift along its length, leaving some parts locked for unusually long periods. These patterns emerge only in hindsight, traced in geological records of past earthquakes. Uplifted terraces, offset streambeds, disturbed layers of sediment. Such markers speak to the persistence of the forces involved, forces that pay no mind to human time or awareness. The invisible weight of strain is always present, whether in the restless edges of a plate boundary or in the quiet interior of a stable continent, where intraplate faults gather tension without fanfare. Even in the absence of shaking, the crust is in motion, storing the story of its next release in bonds too deep and too strong for human senses to detect. And so the land waits not in expectation, but in inevitability, holding within it the silent compression of years, centuries and millennia, until the balance shifts and motion returns in a sudden unstoppable wave. When the stored strain in the crust finally exceeds the strength of the rocks that hold it, the locked fault does not ease open gradually but breaks with startling suddenness. This is the moment of elastic rebound, when the deformed rock masses on either side of the fault snap back toward a position of lower stress, releasing decades or centuries of accumulated energy in seconds. In those brief instants, the landscape shifts sometimes by only a few millimeters, other times by several meters depending on the length of the rupture and the magnitude of the stored strain. The elastic rebound theory, first articulated after the Great Earthquake in San Francisco in 1906, remains one of the most enduring principles in seismology, describing how the crust behaves like a bent and twisted beam that finally fractures and springs back toward its original shape. Yet the moment of failure remains unpredictable. The physics is clear, but the conditions at depth hidden from view determine the precise second when the bonds within the rock will give way. One quiet irony lies in the fact that an earthquake is not the release of all strain but only part of it. Much remains locked within the fault zone to be added to again as the plates continue their relentless motion. Another irony is that even when the rupture occurs, the two sides of the fault do not slide smoothly, but catch and grind, producing smaller shocks and leaving pockets of strain behind. And another still is that while the rupture is almost instantaneous, the preparation for it spans lifetimes, generations, and entire historical eras. The sudden unfastening of a fault sends seismic waves outward in all directions, carrying the energy of the break through rock layers and along the surface. Near the fault, the displacement may be visible in scarps offset roads or shifted river channels. In deeper or less accessible places, the rupture leaves no obvious mark on the surface, yet still shakes the land far away. The amount of slip along the fault varies along its length, often greatest at the centre of the rupture, and diminishing toward its ends, a pattern shaped by the geometry of the fault and the frictional properties of the rocks. At the moment of break, minerals along the fault plane may grind into ultrafine powder, producing a layer of fault gouge that can act as both a lubricant for movement and a barrier to the passage of fluids. The speed of rupture can reach several kilometers per second, fast enough that the seismic waves it generates outrun the human ability to process what is happening. But deep inside the crust, the movement is governed not by urgency, but by the immutable laws of friction and elasticity. The rupture may begin at a single point, the hypercenter, and then spread outward along the fault plane in a cascade of breakage. In some earthquakes, this rupture may stop abruptly when it reaches a section of the fault with higher strength or a different orientation. In others, it may leap to connected fault segments, enlarging the event into a complex multi-fault rupture. These details remain the subject of careful study, for they influence not only the shaking experienced on the surface, but also the pattern of aftershocks that follow. The quiet mystery that endures is why certain faults break in full-length ruptures, while others release strain in smaller patchwork events. Seismologists can model the process in laboratory rock samples and computer simulations, but the irregularity of real-world faults resists precise forecasting. The analogy of a zipper is sometimes used. Some ruptures unzip the fault from one end to the other, others open only partway before catching again. Yet the zipper in this analogy is buried kilometers deep, invisible and inaccessible, its condition known only from indirect measurements. In the largest earthquakes, the displacement can reshape the landscape. Coastal terraces may rise abruptly above the tide line, while inland valleys sink, changing the course of rivers and altering drainage patterns. In subduction zones, A megathrust rupture can displace the seafloor upward by several meters, pushing vast volumes of water outward to form tsunamis that cross entire ocean basins. In strike-slip settings, the horizontal offset of roads, fences, and stream channels becomes a quiet testimony to the force of the event, a visible reminder that solid ground is not truly fixed. Yet even the most dramatic ruptures leave no sign in many places, especially in regions of thick vegetation, rapid erosion, or human alteration of the land. The rupture is also uneven in its release of energy. Near the hypocenter, the sudden motion generates intense high-frequency shaking, while farther from the source the energy arrives in slower rolling waves. The duration of shaking depends on the length of the rupture. The largest earthquakes can continue for several minutes, though most last less than a minute. The human sense of time during such an event is distorted, yet the geological clock records only the instant of release and the long span of stillness that follows. This contrast between the brevity of the rupture and the vastness of its preparation is one of the enduring ironies of seismic processes. Another is that the same physical principles apply to both the smallest and the largest earthquakes. The difference lies only in scale. A microquake along a minor fault in a remote area and a magnitude 9 rupture along a subduction zone both arise from the same interplay of stress friction and elasticity. Once the rupture ceases, the fault enters a new state of balance. The elastic rebound has relieved some of the accumulated strain, but the plates continue to move, beginning the cycle again. The crust may settle with small aftershocks as the surrounding rock adjusts to the changed stress field. In some cases, the release of strain in one area increases the stress on an adjacent segment, bringing it closer to its own failure. This transfer of stress links earthquakes across distances and times, creating patterns that unfold over decades and centuries. Yet not all ruptures lead to immediate neighbors breaking. Some faults remain silent for centuries after nearby events holding their strain for another cycle. The sudden unfastening of a fault is in geological terms a brief punctuation in an unending sentence, a momentary shift in a structure that has been building and rebuilding itself for millions of years. Seen from this perspective, the rupture is not an end nor even a beginning, but a single step in the quiet and relentless movement of the Earth's crust. The surface may bear new scars, but the deeper processes continue without pause, guided by forces that operate far beyond the scale of human time. In this way, the act of elastic rebound is both final and provisional, closing one chapter of strain while opening another in a cycle that will repeat for as long as the plates drift across the surface of the planet. Beneath the thin veneer of soil and vegetation, the crust is cut by fractures that extend for kilometers, plains where rock masses have slipped past each other under the pressure of tectonic forces. These are faults, and among them the strike-slip variety is one of the most striking in its geometry and effect. In a strike-slip fault, the motion is primarily horizontal, with the two sides sliding laterally past one another. The displacement may be only a few centimeters in a small earthquake, or several meters in a major event, but the principle remains the same, a release of built-up strain along a nearly vertical fracture. Famous examples include the San Andreas Fault in California and the North Anatolian Fault in Turkey, each marking the boundary between large tectonic plates whose horizontal motions are locked for years before slipping in sudden bursts. The motion along a strike-slip fault is classified as right lateral or left lateral, depending on the relative direction of movement when viewed from one side. This distinction is simple in description, but complex in the field, where the actual motion may be oblique, incorporating small vertical components. The quiet irony of strike-slip faults is that they can produce devastating shaking without altering the elevation of the land in any obvious way. Another is that their surface traces can be narrow and subtle, hidden beneath farmland or urban development, even as they represent deep structures that extend through the brittle crust. And another still is that the apparent simplicity of their motion conceals intricate networks of subsidiary fractures, bends, and step-overs that influence the behavior of each rupture. Along their length, strike-slip faults often exhibit offset landforms that record the cumulative effect of repeated earthquakes. Streams are deflected, sideways ridges are sliced, and man-made features like roads and fences are abruptly shifted. These offsets may persist for centuries, slowly erased by erosion and vegetation, or preserved in arid landscapes where change is slow. At bends in the fault, the motion can create zones of compression or extension. A restraining bend forces the crust upward, forming small mountain ranges, while a releasing bend pulls the crust apart, generating low basins or sag ponds. These features add complexity to the stress field along the fault, influencing where future ruptures might begin or end. The geometry of a strike-slip fault is rarely a single straight line. Instead, it is often segmented, with each segment capable of rupturing independently or in combination with others. Historical records and paleoseismic studies show that some earthquakes rupture only part of a fault, while others link multiple segments in a single, much larger event. The decision of the fault to break in one way or another is governed by the distribution of stress, the frictional properties of the rocks, and the subtle influence of previous earthquakes. This remains one of the quiet mysteries of fault mechanics, why certain earthquakes cascade through multiple segments, while others stop abruptly. Seismic waves generated by strike-slip ruptures travel efficiently through the crust, carrying strong shaking to great distances. Because the movement is lateral, the pattern of shaking is often asymmetric with greater intensity along the direction of rupture propagation. In large events, this can lead to pronounced directivity effects, where the ground motion is amplified in the path of the moving rupture front. These physical processes are invisible to casual observation, yet they shape the hazard posed by each segment of the fault. Geophysical imaging reveals that strike-slip faults are not uniform surfaces, but complex zones containing multiple strands, gouge-filled cores, and blocks of relatively intact rock. These internal structures can localize strain in certain places, alter the speed of rupture, and control the distribution of aftershocks. In some cases, creeping sections relieve strain, gradually moving a few millimeters each year, without generating large earthquakes. The San Andreas Fault, for example, has a well-known creeping segment near Parkfield, where steady slip contrasts sharply with the locked segments to the north and south. This creeping motion is another irony. It prevents the build-up of large earthquakes in that section, but it transfers strain to the locked parts of the fault, potentially hastening their eventual rupture. The study of strike-slip faults also extends into the deep past. For many ancient shear zones now preserved in continental interiors were once active plate boundaries. In these places, the rocks record a history of horizontal motion through mylonites, cataclasites, and foliated fault rocks, their minerals reoriented and recrystallized by the intense shear. These fossil faults tell of plate motions that no longer exist, offering a reminder that the present arrangement of boundaries is temporary. Even the most prominent active strike-slip faults will one day be abandoned as plate motions evolve and new boundaries form elsewhere. In the meantime, the surface expression of these faults continues to evolve, shaped by both sudden ruptures and the slower processes of erosion, sedimentation, and human alteration. Urban areas built across strike-slip faults face unique challenges, for the narrow but deep rupture zones cannot be reinforced or engineered away. Instead, infrastructure must be designed to accommodate potential offset, and land use planning must consider the inevitability of future displacement. Yet in many places, development proceeds directly over active fault traces, the risk hidden or ignored, until an earthquake redraws the lines. The motion along strike-slip faults is sometimes likened to the sliding of two books past each other on a shelf, a useful analogy for understanding the lateral displacement, but one that fails to capture the immense forces involved. In reality, the frictional resistance of kilometres-thick rock masses is enormous, and the sudden release of that resistance is what generates the seismic energy we feel as an earthquake. The recurrence intervals for large events on strike-slip faults can range from decades to centuries depending on the rate of plate motion and the length of the locked segments. These intervals are irregular, influenced by the interplay of stress transfer from nearby earthquakes, variations in fault geometry, and changes in fluid pressure within the fault zone. Despite advances in monitoring, the precise timing of the next rupture remains beyond current capability. Instruments can record the steady accumulation of strain and detect small earthquakes along the fault, but the transition from locked to ruptured is a threshold crossed in an instant without a clear warning. And so the strike-slip fault waits silent beneath the land, its next movement already prepared in the invisible shifting of minerals and the slow, relentless push of the plates. When it moves, it will do so without hesitation, sliding past in a brief but powerful gesture that is only one more step in the endless rearrangement of the crust. The horizontal nature of this motion may leave the elevation unchanged, but the map itself will have shifted, and the offset will stand as another record in the long archive of geological change, a mark left by the deep patient forces that shape the planet in their own unhurried rhythm. When tectonic forces push two crustal blocks toward each other, the resulting structures are thrust faults, where one block is driven upward and over the other in a movement that shortens and thickens the crust. These faults are most commonly found in convergent plate boundaries such as subduction zones and continental collision zones, where the relentless convergence of plates builds mountain ranges and uplifts high plateaus. The mechanics are straightforward in concept. Compressional stress causes rock layers to fracture and slip along inclined planes, with the hanging wall moving up relative to the footwall. Yet in practice, thrust faults are intricate systems with multiple branches and ramps that distribute strain unevenly. Some segments lie deep below the surface, concealed beneath layers of younger rock, while others break through to daylight, forming visible scarps. The quiet irony of thrust faults is that their greatest work is often invisible, hidden under the mountains they build. Another irony is that these structures which raise land into the sky are also responsible for some of the deadliest earthquakes in history. And still another is that the higher the mountains grow, the more their weight presses downward, influencing the very faults that lifted them. In continental collision zones such as the Himalayas thrust, faulting accommodates the immense northward push of the Indian plate into Eurasia. The main Himalayan thrust, a vast fault system running beneath the range, stores strain for decades or centuries before releasing it in powerful earthquakes that can shake entire regions. These ruptures may propagate for hundreds of kilometers, producing ground displacements measured in meters. Yet the uplift they produce is not a sudden creation of mountains. Rather, it is one moment in a cycle of deformation that has been ongoing for tens of millions of years. In subduction zones, thrust faults form where one plate dives beneath another and the upper plate is compressed and warped. These megathrust faults can generate the largest earthquakes known, with magnitudes exceeding 9, as occurred in Chile in 1960, Alaska in 1964, and Japan in 2011. In these events, the seafloor above the fault is thrust upward sometimes by several meters, displacing vast volumes of seawater and producing tsunamis that cross ocean basins. The combination of sudden uplift and subsequent water movement can reshape coastlines, inundate low-lying areas, and leave lasting geomorphic signatures. The structure of thrust faults is often more complex than a single inclined plane, Many consist of a series of connected segments with ramps that cut upward through rock layers and flats that follow weaker horizons. This geometry can cause the rupture to jump between segments, producing variations in the amount of slip and the distribution of shaking. The presence of multiple splay faults branching from the main thrust adds further complexity, for these splays can also rupture, sometimes amplifying local ground motion. One quiet mystery is why some thrust faults release their strain in a single massive rupture, while others fail in smaller piecemeal events. Laboratory experiments and numerical models suggest that factors such as fault roughness, sediment thickness, and fluid pressure can influence the mode of failure. But the interplay of these elements in the natural setting is not yet fully understood. Thrust faulting is not confined to plate boundaries. Intraplate settings can also host them, particularly in regions of crustal shortening, due to far-field tectonic forces. These faults may have long recurrence intervals, making their hazard difficult to assess, yet they are capable of producing damaging earthquakes when they do slip. Because thrust faults often dip at low angles, their rupture surfaces can extend far horizontally, allowing large areas of rock to move simultaneously. This geometry also means that the shaking from thrust earthquakes can be felt over broad regions, sometimes hundreds or thousands of kilometers from the epicenter. The landforms created by thrust faulting evolve over time. Fresh scarps may be softened by erosion, while uplifted terraces record past episodes of movement. In mountainous regions, the interplay of tectonic uplift and surface processes such as landsliding river incision and glacial erosion continually reshapes the topography, yet the underlying structure remains ready to accommodate the next increment of convergence. In some thrust fault systems, there are creeping sections where slow aseismic slip occurs, relieving strain without generating large earthquakes. This movement can be detected only with precise geodetic instruments, and it contrasts sharply with the locked segments where strain builds until it is released suddenly. The coexistence of creeping and locked sections along the same fault adds complexity to hazard assessment, for the boundaries between them can influence how ruptures propagate. Human observation of thrust faulting is often limited to its consequences. The ground may suddenly tilt, changing the flow of rivers or draining lakes. Hillsides may be thrust upward, splitting forests or cropland. In subduction zones, coastal land may rise permanently above the reach of tides, while in other areas the ground subsides, allowing the sea to encroach. These changes, though dramatic in the human perspective, are modest in the geological scale, yet they accumulate over millions of years to build some of the planet's most prominent features. There is a quiet irony in the fact that the forces responsible for these changes operate continuously, even during the long intervals when no earthquake occurs. The plates press together without pause, the faults hold their strain, and the mountains grow by fractions of a millimeter each year. When the rupture comes, it is a brief release, after which the process resumes exactly as before. Thrust faults also interact with other fault types. In oblique convergence zones, they may be linked to strike-slip faults that accommodate the horizontal component of motion, creating a network of interconnected structures. The transfer of stress between these faults can trigger sequences of earthquakes across different styles of faulting, revealing the interconnected nature of crustal deformation. While modern seismology can map the geometry of thrust faults and measure their rate of strain accumulation, predicting the exact timing of rupture remains out of reach. The complexity of fault surfaces, the variability of rock properties, and the role of fluids at depth all contribute to the uncertainty. What is certain is that as long as plates converge, thrust faults will continue to operate, lifting land, shaping coasts, and in moments of sudden release sending seismic waves outward to remind the surface that the mountains are still growing. Each earthquake along a thrust fault is one more note in a long, slow composition the rhythm of convergence measured not in beats, but in centuries the melody written in the rise and fall of the land itself. Where the crust is pulled apart rather than pushed together, the result is a normal fault, a structure in which the hanging wall block moves downward relative to the footwall along a dipping fracture. These faults form in extensional tectonic settings such as continental rift zones, back-arc basins, and regions of post-orogenic collapse, where the crust once thickened by compression relaxes and spreads. The mechanics are driven by tensional stress that stretches the crust beyond its ability to deform elastically, causing it to fracture and slip. The displacement is primarily vertical, though small horizontal components may be present depending on the local stress field. The quiet irony of normal faults is that they often create striking topography, while representing a kind of geological letting go, the crust yielding and thinning, rather than building and thickening. Another irony is that while they lower one side of the landscape, they simultaneously raise the other, producing steep fault scarps and high-standing footwalls. A third irony lies in the fact that some of the most dramatic landforms they create, such as rift valleys, are evidence not of stability but of progressive separation. Normal faults can be simple planar structures, or they can form as part of complex systems in which multiple faults accommodate the extension. In continental rifts such as the East African Rift, large normal faults bound elongated valleys that can be hundreds of kilometers long and tens of kilometers wide, with flanking escarpments rising more than a kilometer above the valley floor. These rifts often contain active volcanoes as the stretching crust allows magma to rise along fractures. In such settings, faulting and magmatism are closely linked, each influencing the other's location and activity. The geometry of normal faults typically involves a high-angle dip, often between 45 and 70 degrees, though at depth, the fault may flatten into a detachment surface that accommodates the bulk of the displacement. In some regions, low-angle normal faults, known as detachment faults, extend for tens of kilometers, bringing deep crustal rocks to the surface and exhuming metamorphic cores. These low-angle structures are the subject of ongoing debate in structural geology, for their slip behavior challenges traditional models of frictional stability. One quiet mystery is why some rift zones evolve into full ocean basins, while others stall and remain as continental depressions. The reasons likely involve the balance between mantle upwelling crustal rheology and the regional stress field, but the interplay of these factors remains incompletely understood. Normal faults produce distinctive surface expressions. Fresh scarps may be visible after an earthquake cutting across roads, fields, and river channels. Over time, erosion modifies these scarps into triangular facets, while sediment from the hanging wall accumulates at the base of the footwall to form alluvial fans. In some extensional basins, repeated movement along normal faults creates stair-stepped topography with a series of parallel ranges and intervening valleys. Basin and Range Province in the western United States is a classic example, its landscape shaped by millions of years of repeated faulting. Earthquakes on normal faults can be powerful, though their magnitudes are often slightly lower than those of the largest thrust events due to the generally smaller fault areas involved. Still, they are capable of producing destructive shaking, especially in populated rift valleys, where the ground motion may be amplified by basin sediments. The shaking pattern from a normal fault earthquake is influenced by the dip of the fault and the direction of rupture propagation. In some cases, the vertical displacement can be significant enough to alter local hydrology, changing the course of rivers or creating new lakes. Normal faults do not act in isolation. They interact with adjacent faults through the redistribution of stress. Movement on one fault can load or unload neighboring structures, potentially triggering sequences of earthquakes across a fault network. This interplay is evident in active rift, where swarms of earthquakes may migrate along the rift axis, each event adjusting the local stress field. The recurrence intervals for large earthquakes on normal faults vary widely, from decades in rapidly extending regions to many thousands of years in slower systems, because the surface expressions of these faults can be subtle and degraded over time. Paleoseismology plays a critical role in reconstructing their history. Trenching across fault scarps can reveal displaced layers of sediment, each marking a past rupture. These records help establish the timing and magnitude of prehistoric earthquakes, offering insight into the long-term behavior of the fault. There is a quiet irony in the fact that while normal faults lower landscapes, they also provide windows into deep geological history. The uplifted footwalls expose older rocks, sometimes revealing sequences of strata and metamorphic assemblages that would otherwise remain buried. In this way, extension not only reshapes the surface but also discloses the structure and composition of the crust. In oceanic settings, normal faulting is common along the flanks of mid-ocean ridges, where the newly formed crust bends and cracks as it cools and moves away from the spreading center. These underwater normal faults can form impressive escarpments, though they are hidden from direct view beneath the sea. Submersible and remote sensing studies have mapped many such features, showing that the processes of extension are as active beneath the oceans as they are on land. In volcanic rift zones, normal faults may accommodate the outward spreading of the volcanic edifice, a process driven by both gravity and magmatic intrusion. The interaction between faulting and volcanism in these settings can produce complex hazards, as earthquakes may precede or accompany eruptions, and fault movement can alter the pathways for magma ascent. The development of normal fault systems is an ongoing process, with faults initiating linking and dying out over geological time. The stress field in a region can shift, changing the orientation and activity of the faults. Some rift systems eventually evolve into passive margins as the continental crust breaks apart and new oceanic crust begins to form between the diverging fragments. Others remain as zones of low relief and subdued tectonic activity, their faults preserved in the geological record but no longer active. The land shaped by normal faults bears the imprint of both sudden and gradual change. Each earthquake is a discrete event, altering the elevation and relief in seconds, yet the overall extension unfolds over millions of years, creating broad valleys, isolated ranges, and tilted blocks. From the human perspective, the sudden drops and uplifts are dramatic interruptions to daily life. From the geological perspective, they are routine adjustments in a vast and continuous reconfiguration of the crust. In the long stillness between ruptures, the valleys deepen, the mountains erode, and the scarps soften, but the forces of extension do not vanish. They continue unhurried and persistent, preparing the next movement in a sequence that will outlast every generation that witnesses it. Not all faults fit neatly into the categories of purely horizontal or purely vertical motion. In many places, the crust moves in a way that combines both, producing what are known as oblique slip faults. These structures accommodate displacement in two directions at once, a horizontal component like a strike-slip fault and a vertical component like a normal or thrust fault. The result is a single rupture that shifts the land sideways and up or down depending on the orientation of the stress field. Such faults are common where the plate motions are neither perfectly head-on nor perfectly parallel, but instead occur at an angle. The quiet irony of oblique slip faults is that they rarely declare themselves with one clear signal. Instead, they leave a mixed imprint on the land, part lateral offset and part change in elevation, making their movements harder to read from surface evidence alone. Another irony is that while their complexity makes them challenging to study, the very same complexity allows them to accommodate strain more efficiently than faults restricted to one type of motion. And a third is that the interaction of vertical and horizontal movement can create landforms that appear to contradict one another, uplifted ridges lying next to offset streambeds, or deep basins flanked by elevated terraces. Oblique slip motion occurs in a variety of tectonic settings. At some subduction zones where the trench is angled relative to the plate motion, the interface between plates experiences both thrusting and strike-slip movement. This can generate earthquakes with complex rupture patterns where part of the fault pushes one plate over the other, while another part shears them laterally. In continental interiors, oblique slip faults may form where regional stress fields are reoriented over time or where two fault systems intersect, forcing the crust to respond with a compromise between competing motions. The geometry of an oblique slip fault is defined by its rake, the angle between the slip direction and the horizontal strike of the fault. A rake of 0 degrees is pure strike slip, 90 degrees is pure dip slip, and oblique slip falls somewhere in between. Determining the rake from field evidence involves measuring offset features of known orientation, but this is rarely straightforward, especially when erosion deposition and human alteration have obscured the original forms. Geophysical methods such as focal mechanism solutions from seismic wave data can provide more direct insight, revealing the orientation of the fault plane and the direction of slip during an earthquake. One quiet mystery in the study of oblique slip faults is how the relative proportions of vertical and horizontal motion evolve over time. Some segments may begin with predominantly one type of motion and gradually shift toward the other as the regional stress field changes. Others maintain a stable balance for millions of years, suggesting a persistent alignment between plate motion and fault orientation. This variability complicates efforts to model future behavior for the past, is not always a perfect guide to the future in such mixed-mode systems. The surface expressions of oblique slip faults are often varied and complex. In one stretch, a fault may produce a scarp that lifts one side above the other. In the next, it may offset a river channel or a road laterally. Where the vertical component dominates, basins and ranges may form much as in normal or thrust faulting. Where the horizontal component is stronger, narrow linear valleys or shutter ridges may appear similar to features along strike-slip faults. The juxtaposition of these landforms can make it difficult to trace the fault's path without detailed mapping. Earthquakes on oblique slip faults tend to produce more complicated ground motion than those on faults with purely one type of slip. The combination of vertical and horizontal movement can affect structures in different ways, pulling them in one direction, while also lifting or dropping their foundations. This compound motion may also generate a broader range of seismic waves, influencing how the shaking is felt at various distances. In coastal settings, the vertical component of oblique slip motion can raise or lower the shoreline, altering tidal patterns and coastal ecosystems. The horizontal component may simultaneously shift river mouths or displace harbours, creating compound challenges for navigation and settlement. In some cases, the uplifted blocks from repeated oblique slip motion can become sites of erosion and sediment supply, feeding nearby basins that were themselves created by the fault's subsidence. Oblique slip faults are also important in the transfer of stress between different fault systems. Because they can accommodate motion in multiple directions, they often act as links between faults of different styles. A strike-slip system may feed into an oblique slip fault that in turn connects to a thrust system, allowing strain to move through the crust along a path of mixed geometries. This linking role can make oblique slip faults critical to the broader tectonic behavior of a region, influencing where and when large earthquakes occur. The recurrence intervals for significant earthquakes on oblique slip faults vary widely depending on the rate of plate motion, the size of the fault segments, and the proportion of motion taken up by a seismic creep. In some cases, the fault may release its strain in moderate earthquakes every few decades. In others, it may remain locked for centuries before producing a major rupture. The variability in motion style adds further uncertainty to hazard assessment, for the damage potential depends not only on the magnitude of the event, but also on the mix of vertical and horizontal displacement. There is a quiet irony in the fact that while oblique slip faults seem by definition to be neither one thing nor the other, they are often among the most geologically efficient structures. By accommodating two components of motion at once, they reduce the need for multiple faults to handle the same stress field, yet they also concentrate strain in ways that can lead to particularly complex and damaging earthquakes. Over long timescales, oblique slip motion can build intricate landscapes. Mountains may rise while valleys shift sideways. River networks may become skewed and distorted. Sedimentary basins may migrate laterally while continuing to deepen. The end result is a geological record in which structures and landforms bear the combined imprint of uplift subsidence and lateral translation. For the observer standing on such a fault trace, it is easy to miss the complexity underfoot. A linear valley may suggest strike-slip motion, while the tilted strata in a nearby hillside hint at vertical displacement. Only when the patterns are assembled across many kilometers does the oblique nature of the movement become clear, and even then the understanding is incomplete, for the next earthquake may emphasize a different component, leaving the landscape to tell a slightly different story. In the stillness between these events, the plates continue their angled approach, the minerals in the fault zone slowly adjusting the frictional resistance, gradually rising toward another failure. When the rupture comes, it will not choose between moving up or moving sideways. It will do both, as it always has, shifting the ground in a way that defies simple description, yet fits precisely into the quiet, unbroken logic of the planet's ongoing reshaping. When a fault ruptures, the stored energy is transformed into vibrations that travel outward through the planet as seismic waves. These waves are not all the same. They move in different ways at different speeds and through different layers of the Earth. The fastest are primary waves or compressional waves, which push and pull the material they move through in the same direction as their travel. They are the first to arrive at seismic stations racing through the crust and mantle at speeds of 5 to 8 kilometers per second. Because they can pass through both solids and liquids, they travel through the entire interior, bending and changing speed as they encounter materials of different density. Following them are secondary waves or shear waves, which move the ground perpendicular to their direction of travel. They are slower, moving at about 3 to 4 kilometers per second, and cannot travel through liquids, which is why they do not pass through the outer core. The quiet irony of shear waves is that although they arrive second, they often cause greater shaking damage than the faster primary waves. Another irony is that the most destructive waves of all are not the first or second to arrive, but the slowest, the surface waves that ripple along the boundary between the solid earth and the open air. And a third irony is that the path of a seismic wave is determined by materials deep underground that no human eye has seen, yet its effects are most keenly felt at the surface. Surface waves include two main types: love waves, which move the ground horizontally in a side-to-side motion, and Rayleigh waves, which roll like ocean swells, moving both vertically and horizontally in an elliptical pattern. These waves are slower, still travelling at speeds of 2 to 3 kilometers per second, but because they are confined to the shallow layers of the crust, they can retain high amplitudes over long distances. In large earthquakes, surface waves can circle the planet multiple times, gradually diminishing as they lose energy to friction and scattering. The interaction of seismic waves with the structure of the Earth is complex. At boundaries between layers of different density or rigidity, waves are reflected, refracted, or converted from one type to another. A primary wave encountering such a boundary may produce a secondary wave and vice versa. This behavior allows seismologists to use earthquake waves as probes mapping the interior, much like medical imaging uses sound waves to map the inside of the human body. The arrival times of different waves at seismic stations around the globe are plotted as seismograms patterns of ground motion that reveal the distance to the earthquake source and, with enough stations, its exact location. The speed differences between primary and secondary waves create a time gap in arrivals that grows with distance. This gap is one of the tools used to issue early warnings, for sensors can detect the harmless primary waves and estimate how much time remains before the slower, more damaging waves arrive. One quiet mystery is how much fine-scale structure in the crust and mantle influences the shaking experienced in a specific location. Variations in rock-type fault complexity and topography can focus or disperse seismic energy, making some areas experience intense shaking, while others nearby remain relatively still. Even modern numerical models cannot yet account for all these variations, and so the exact pattern of shaking remains partly unpredictable. The travel paths of seismic waves also reveal the larger structure of the planet. The absence of secondary waves on the far side of the globe from a large earthquake led to the discovery that the outer core is liquid, while the bending of primary waves indicated that the core has a different composition and density than the overlying mantle. More refined observations have shown that the inner core is solid but anisotropic, meaning it transmits waves faster in some directions than others. These discoveries come not from drilling or direct observation, but from interpreting the subtle timing and shapes of waves recorded at thousands of seismic stations. The generation of seismic waves begins at the rupture front, where the fault slips and releases stored strain. The abrupt motion sends out a spectrum of frequencies, from high-frequency waves that rattle buildings to low-frequency waves that can sway tall structures and bridges over great distances. The balance of these frequencies depends on the size and speed of the rupture, the depth of the fault, and the properties of the surrounding rock. In the largest earthquakes, low-frequency waves can dominate, producing long rolling motions that persist for minutes and travel across continents. The recording of these waves has become a global effort. Networks of seismometers on land instruments anchored to the seafloor, and even sensors attached to the fiber optic cables of the internet all contribute to monitoring seismic activity. The data are not only used to study earthquakes, but also to detect underground explosions, track volcanic activity, and monitor the movement of ice sheets. In this way, seismic waves serve as a universal messenger, carrying information about a wide range of geological processes. There is a quiet irony in the fact that the same waves that can topple cities are also our primary source of knowledge about the planet's deep structure. The damaging potential of seismic waves depends on more than just their amplitude. The duration of shaking, the frequency content relative to the natural frequencies of structures, and the local ground conditions all play roles. Soft sediments can amplify certain frequencies, increasing shaking in valley floors compared to nearby bedrock ridges. In some cases, the resonance between the wave frequencies and the height of buildings can magnify damage dramatically. These site effects are an active area of research, for they hold the key to improving earthquake-resistant design. Surface waves, with their slow decay over distance, can carry destruction far from the epicenter. The 1976 Tangshan earthquake in China caused severe damage hundreds of kilometers from its source, largely due to strong surface waves traveling through relatively uniform crust. In contrast, complex crustal structures can scatter and weaken these waves, reducing their reach, but sometimes concentrating their energy in specific areas. Understanding these patterns is crucial for seismic hazard assessment. Yet the variability is such that no two earthquakes produce identical shaking, even if they occur on the same fault segment. Seismic waves are part of the cycle of strain accumulation and release that defines earthquake activity, yet they are also part of a much broader story. They remind us that the Earth is an elastic body capable of storing and releasing energy across scales, from the smallest microquake to the largest megathrust event. In the stillness between earthquakes, the planet remains in quiet motion, with stresses building and waves yet to be born. When the next rupture comes, the sequence will begin again, a silent build-up, an abrupt break, and the launch of waves that will travel through the deep across oceans and under continents, carrying the unmistakable signature of the fault that set them free. Along the curving margins of the oceans lie subduction zones, places where one tectonic plate bends and descends beneath another, sinking into the mantle over distances of hundreds of kilometers. Here the boundary between plates is not a narrow fracture, but a vast, sloping interface capable of locking over lengths of 1,000 kilometers or more. When this interface slips suddenly, the result is a megathrust earthquake, the most powerful type known, with magnitudes that can exceed 9, and durations of shaking measured in minutes. The quiet irony of subduction zones is that they create the deep trenches that mark their presence. Yet the most dangerous parts lie far below, invisible to even the deepest ocean. Another irony is that these zones, which recycle oceanic crust into the mantle, also give rise to volcanic arcs and the formation of new continental crust. And a third irony is that they can remain silent for centuries, storing strain with no visible sign until a single rupture changes coastlines in moments. The mechanics of subduction involve the descent of dense oceanic lithosphere beneath a less dense plate, driven by the pull of the sinking slab and the push from the mid-ocean ridge far behind it. At the interface, friction and irregularities in the fault surface cause it to lock in places, preventing steady motion. Over decades or centuries, strain accumulates until it exceeds the strength of the fault, at which point the interface slips abruptly. The release of strain in a megathrust rupture is immense, often involving tens of meters of relative displacement over an area larger than many countries. This sudden movement displaces large volumes of seawater. If it occurs offshore, producing tsunamis that can cross entire ocean basins. In the 2011 Tohoku earthquake off Japan, the seafloor was thrust upward by several meters, sending waves across the Pacific and inundating coastal areas within minutes. The fault slip also moved parts of Japan several meters eastward, altering the shape of the island permanently. Subduction zones are distributed unevenly around the globe, concentrated along the so-called Ring of Fire encircling the Pacific Ocean. Notable examples include the Cascadia subduction zone off North America, the Peru-Chile Trench along South America, the Sunda Trench in Indonesia, and the Tonga Trench in the Southwest Pacific. Each has its own history of great earthquakes and tsunamis recorded both in human accounts and in the geological record. In places like Cascadia, tree rings and coastal marsh deposits preserve evidence of sudden land subsidence and saltwater intrusion from past megathrust events centuries ago. These records show that even in regions with no instrumental history of large earthquakes, the potential remains locked beneath the ocean floor. One quiet mystery of subduction zones is the irregularity of their cycles. Some segments rupture every few centuries in events of similar size, while others vary widely in timing and magnitude. The reasons for this variability may lie in differences in sediment thickness, fluid pressure, slab geometry, and the presence of splay faults branching from the main interface. These splays can rupture alongside the main fault, increasing uplift and tsunami generation in certain areas. The role of fluids is particularly important. As the subducting plate descends, it releases water from hydrated minerals, which can migrate upward into the fault zone, reducing friction and potentially triggering slip. This process may help explain the occurrence of slow slip events in some subduction zones, where the fault moves over weeks or months without generating strong shaking. These events can alter the stress on adjacent locked sections, sometimes bringing them closer to failure. The vertical and horizontal components of motion in a megathrust earthquake vary along the rupture, producing a patchwork of uplift and subsidence along the coast. In the 1960 Chile earthquake, parts of the coastline rose by more than 2 meters, while others sank by a similar amount. These changes altered tidal patterns, transformed estuaries, and forced communities to adapt to new shorelines. In the longer term, repeated cycles of uplift and subsidence can create marine terraces and drowned forests, leaving a geomorphic record of the fault's behavior over thousands of years. The shaking from a megathrust event can last several minutes, long enough to cause cumulative damage as structures sway back and forth. The low-frequency energy from such large ruptures travels great distances, shaking tall buildings far inland and even affecting regions on the far side of the ocean basin. Because the rupture area is so large, different parts of the fault may experience different slip speeds, producing complex patterns of seismic radiation. Understanding these patterns is key to improving tsunami forecasts, which depend on knowing how much of the seafloor moved and in which direction. There is quiet irony in the fact that the same process that drives megathrust earthquakes also plays a role in building continents. Magmas generated by the melting of the mantle wedge above the subducting slab rise to feed volcanic arcs, adding material to the overriding plate. Over millions of years, this accumulation contributes to continental growth, even as the same boundary occasionally produces catastrophic earthquakes and tsunamis. Subduction zones also link the surface with the deep earth in ways that extend beyond seismic hazards. The subducted plate carries sediments, oceanic crust, and seawater into the mantle, recycling material into the planet's interior and influencing the long-term chemical evolution of the Earth. The deep earthquakes that sometimes occur within the subducting slab, far below the seismogenic zone of the megathrust, are another reminder of the complex processes at work. While these deep quakes do not typically cause damage at the surface, they reveal the ongoing deformation of the slab as it bends and descends into the mantle transition zone. In the stillness between megathrust events, the plates continue their slow convergence, pressing together along the locked interface. Geodetic measurements record this motion, showing that coastal areas are gradually being compressed and shifted landward. These measurements are crucial for estimating how much strain has accumulated and how much might be released in the next rupture. Yet they cannot tell exactly when that release will come, for the fault's internal state remains hidden from view. Subduction zones are reminders of the planet's dual nature, creative and destructive, building new crust and reshaping continents, while also generating some of the most devastating natural disasters. This cycle of locking strain accumulation and sudden release is part of the ongoing motion of the plates, a process that will continue as long as the mantle convects and the oceanic crust cools and sinks. In the moment of rupture, centuries of quiet motion resolve in a few minutes of profound change. The coastline may shift, the seafloor may rise, and the ocean may surge inland, carrying with it the unmistakable signature of the deep interface where two plates meet. And then the silence will return, the plates will press together again, and the long preparation for the next event will begin unnoticed, except by the instruments and the patient records kept by those who know that in subduction, zone stillness is never the same as rest. Not all movements along subduction interfaces or other large faults announce themselves with shaking that can be felt. In recent decades, scientists have identified a class of events known as slow-slip earthquakes, in which a fault surface moves over days, weeks, or even months, releasing strain without generating strong seismic waves. These silent earthquakes were first detected in the early 2000s in subduction zones such as Cascadia in North America and Hikurangi in New Zealand, revealed through precise geodetic measurements that showed coastal areas shifting by centimeters over time without any notable ground motion. The quiet irony of slow slip events is that they can release as much or more total energy as a moderate earthquake, yet most people never notice them. Another irony is that their apparent gentleness does not mean they're harmless. By subtly changing the distribution of stress along a fault, they may bring nearby locked segments closer to failure. And a third irony is that the very stillness of these events, once invisible, has become a crucial part of understanding earthquake cycles. Slow slip events occur in the transition zone between the shallow locked portion of a fault and the deeper section where rocks slide steadily without seismic rupture. This region, lying at depths of tens of kilometers, appears to be subject to frictional conditions that allow for episodic movement without the sudden fracture characteristic of regular earthquakes. The mechanics involve the gradual overcoming of friction as fluid pressure changes or small stress perturbations alter the stability of the fault. Because they produce little high-frequency energy, slow slip events are not picked up by traditional seismometers unless accompanied by a related phenomenon called tectonic tremor, a faint continuous vibration generated by small rapid slips on nearby patches of the fault. This tremor, detectable only by sensitive instruments, is like a background murmur that accompanies the slow motion. The discovery of slow slip events has altered our view of the seismic cycle. In some regions, they recur at fairly regular intervals every year or two, with each event shifting the land surface by measurable amounts. In Cascadia, for example, slow slip events lasting several weeks occur roughly every 14 months, moving the coastline a few millimeters toward the subduction trench before it resumes its steady landward motion as the locked portion of the fault continues to accumulate strain. One quiet mystery is why some slow slip events appear to migrate along the fault over time, as though a moving patch of instability is triggering successive segments to slip. Another is why in some cases they seem to precede large earthquakes, while in others they do not. The relationship between slow slip events and damaging earthquakes remains uncertain. In Japan, a sequence of slow slip episodes was recorded on the Nankai subduction zone in the years leading up to major historical earthquakes, suggesting a possible link. Yet in other subduction zones, slow slip occurs without any immediate seismic consequence. It is possible that the effect depends on the exact location of the slip relative to the locked zone and the stress state of the surrounding rocks. Studying these events in detail requires high-precision GPS networks and borehole strain meters, as well as ocean bottom instruments in offshore settings. Because the movement is so gradual, continuous monitoring is essential to capture the full picture. In some cases, satellites equipped with radar interferometry can detect the subtle surface displacements, providing a wide-area view of the deformation. The data reveal that slow slip is not a rare anomaly, but a regular feature of many plate boundaries hidden until recent advances in measurement made it visible. The presence of fluids appears to play a significant role in enabling slow slip. Water released from the subducting plate can migrate upward into the fault zone, raising pore pressure and reducing the effective normal stress, making it easier for the rocks to slide without abrupt rupture. This mechanism may explain why slow slip is particularly common in subduction settings, where the descending slab continually delivers fluids to depth. However, similar processes have been identified on continental faults, and even in volcanic regions where changes in magma pressure can induce slow fault movement. The implications for hazard assessment are complex. If a slow slip event transfers stress to a locked segment already near failure, it could act as a trigger for a larger earthquake. Conversely, if it relieves enough strain without affecting the locked zone, it might delay the next major rupture. Distinguishing between these scenarios in real time is one of the challenges facing seismologists. The quiet irony is that slow slip events, though imperceptible to most, may hold the key to anticipating changes in seismic hazard. Understanding their triggers Their interaction with regular earthquakes and their variability from one fault system to another is an active area of research. In some places, slow slip is accompanied by deep, low-frequency earthquakes, small events at the base of the seismogenic zone that also appear to be linked to fluid processes. These signals provide additional clues to the conditions at depth, offering indirect glimpses into parts of the fault that cannot be reached directly. Over geological timescales, the cumulative effect of slow slip events may be significant, contributing to long-term plate motion just as steady creep and sudden earthquakes do. This realization challenges the traditional division between seismic and aseismic processes, showing that fault movement exists on a continuum from imperceptible creep to catastrophic rupture. From a human perspective, the slow slip earthquake is a reminder that not all tectonic motion is abrupt or destructive. In the stillness of these events, the Earth moves in ways that change nothing in daily life, but shift the balance of forces deep underground. Like the faint bending of a branch in a steady breeze, these movements escape notice until the branch finally breaks. Whether they act as precursors, companions, or mere bystanders to that break remains one of the quiet questions in modern seismology. In the meantime, the instruments continue to listen, recording the subtle drift of the land and the murmur of tremor far below. Each slow slip event becomes another data point in a growing archive, a hidden chapter in the story of how faults accumulate and release strain. In this way, the invisible is made visible and the silent is given a voice, even if that voice is one of the faintest ever heard from the restless earth. Over the span of decades to centuries, faults follow patterns that, while irregular, hint at a repeating rhythm known as the seismic cycle. This cycle describes the sequence of processes that a fault undergoes between large earthquakes: the slow accumulation of strain, the eventual rupture, and the gradual recovery afterward. In its simplest form, the seismic cycle consists of 3 stages. First is the interseismic period when the fault is locked, and strain builds silently as tectonic plates continue to move. Second is the coseismic stage, the brief moment of rupture, when the stored energy is released as seismic waves. Third is the postseismic phase, in which the crust adjusts to the new distribution of stress through afterslip viscoelastic relaxation and aftershocks. The quiet irony of the seismic cycle is that the stage humans experience most vividly, the earthquake itself, is the shortest by far. Another irony is that the apparent calm of the interseismic period can be a time of intense invisible change at depth. A third irony lies in the fact that even the recovery after an earthquake can redistribute stress in ways that prepare for the next rupture. During the interseismic stage, the locked portion of the fault behaves as though it were fused together, resisting motion, while strain accumulates in the surrounding crust. Geodetic measurements show the land near the fault deforming in response, with points on opposite sides moving slowly in opposite directions relative to one another. This deformation can be measured to millimeter precision over years, offering a way to track the progress of strain accumulation. Yet even with such measurements, the timing of the transition to rupture remains elusive, for the fault's strength and frictional state are not directly observable. When the rupture finally occurs in the coseismic stage, the release of strain is sudden and widespread. Depending on the fault's geometry and the amount of accumulated stress, the rupture may propagate along tens or hundreds of kilometers, with slip ranging from a few centimeters to many meters. In the largest events, the rupture may take several minutes to complete, yet the redistribution of stress is instantaneous compared to the long build-up. This new stress pattern extends beyond the ruptured segment, influencing neighboring sections of the fault and even distant faults through subtle changes in the regional stress field. The postseismic stage begins immediately after the rupture ends. One component of this stage is afterslip, in which parts of the fault that did not fully rupture during the earthquake continue to move, slowly relieving some of the residual strain. Afterslip can last for days, months, or even years depending on the conditions at depth. Another component is viscoelastic relaxation, where the warmer, more ductile lower crust and upper mantle slowly flow to adjust to the new load, causing gradual surface movements that can be detected with precise geodetic instruments. This process can continue for decades, redistributing stress in ways that may either increase or decrease the likelihood of future earthquakes in surrounding regions. Aftershocks are another hallmark of the post-seismic phase. These smaller earthquakes occur as the crust adjusts to the new stress configuration. Their frequency typically decays with time following patterns first described more than a century ago. While most aftershocks are much smaller than the main shock, they can still be damaging if they occur close to populated areas, especially when structures have already been weakened. One quiet mystery is why some faults exhibit relatively regular seismic cycles, producing large earthquakes at intervals of similar length, while others show highly variable timing and magnitude. Geological records of prehistoric earthquakes revealed through trenching and stratigraphic studies suggest that even the most apparently regular faults can have long periods of quiet punctuated by closely spaced large events. Factors such as changes in the stress field fluid pressure and fault geometry can all influence the cycle's variability. The seismic cycle is not confined to large faults at plate boundaries. Intraplate faults far from active margins can also follow long cycles of strain accumulation and release, though their recurrence intervals may span thousands of years. Such faults pose a challenge for hazard assessment, as their long quiet periods can create the illusion of inactivity until a rare powerful earthquake occurs. Understanding the seismic cycle has practical importance for forecasting long-term hazard, even if precise prediction remains impossible. By estimating where a fault is in its cycle and how much strain has accumulated, scientists can identify segments that may be closer to rupture. However, because the cycle is influenced by so many variables, these assessments are probabilistic rather than certain. The cycle is also complicated by interactions between faults. Stress changes from one earthquake can alter the timing of events on nearby faults, effectively resetting or accelerating their cycles. This coupling means that the seismic behavior of one fault cannot be fully understood in isolation. In some cases, large earthquakes have triggered cascades of ruptures across multiple faults within months or years, as occurred in Turkey along the North Anatolian Fault in the 20th century. Observations from GPS networks, INSAR satellites and seismometers are refining our understanding of how strain is stored and released in the seismic cycle. These tools reveal that faults are rarely fully locked or fully creeping. Rather, different sections behave differently, and these behaviors can change over time. This variability suggests that the seismic cycle is less a simple loop than a dynamic system with multiple overlapping processes. There is a quiet irony in how the cycle appears orderly in diagrams, with smooth curves of stress rising and falling, yet is messy and unpredictable in the real Earth. From the human perspective, the seismic cycle is experienced only in fragments. A single lifetime may see one earthquake on a nearby fault, or none at all. For the planet, however, each cycle is just one repetition in an unbroken sequence extending back millions of years. The landscape around us, the ridges, valleys, and coastal terraces, often owes its form to repeated passages through the cycle, each earthquake adding its small measure of change. In the stillness between ruptures, it is easy to imagine that the cycle has stopped, but the plates do not pause. Strain builds invisibly, faults adjust in small ways, and the clock toward the next rupture continues to tick, even if no one can read its exact time. When the next break comes, it will be both a conclusion and a beginning ending one cycle, while setting the next in motion, in a rhythm that will persist for as long as the Earth's crust remains restless. Beneath the threshold of human perception, the crust is alive with countless tiny earthquakes, each releasing a minute fraction of the strain stored in faults. This microseismicity occurs in every tectonic setting, from the mid-ocean ridges to the interiors of continents, and while individual events are too small to cause damage or even be felt together, they form a constant background hum of tectonic motion. The quiet irony of microseismicity is that it reveals the unending activity of the planet's crust even in regions thought of as stable. Another irony is that these tiny quakes often occur in swarms clustering in time and space without leading to any larger rupture. And a third irony is that the most important role of microseismicity may be in what it can tell us about faults that have yet to break in a significant way. Microseismic events have magnitudes below about 2, which is near the threshold of detection by people under ideal conditions. Sensitive seismic networks, however, can detect events much smaller than that recording ground motions on the order of nanometers. These measurements allow scientists to map active fault structures at depth, revealing the geometry and connectivity of fractures that may extend for kilometers. In geothermal regions, microseismicity can occur when fluids are injected or extracted, altering the pore pressure in rocks and triggering small slips on pre-existing faults. Similarly, in volcanic areas, swarms of microquakes can mark the movement of magma or hydrothermal fluids, providing clues to processes occurring far below the surface. One quiet mystery is the relationship between microseismicity and large earthquakes. While swarms sometimes precede major events, they often occur without any significant follow-up, making them unreliable as a predictive tool. In some cases, microseismic activity increases after a large earthquake as the crust readjusts to the new stress state. This aftershock-like activity can continue for weeks or months, gradually tapering off as the fault system settles into a new equilibrium. Foreshock small earthquakes that occur before a main shock are a special case of microseismicity that can be directly linked to a major rupture. In some well-documented sequences, such as the 1975 Haicheng earthquake in China, foreshocks provided a warning that allowed for evacuation. However, many large earthquakes occur without any recognizable foreshock pattern, and many foreshock-like sequences end without a main shock, underscoring the difficulty of relying on them for prediction. The spatial distribution of microseismicity can be revealing. Along major faults, small earthquakes often occur in repeating clusters, rupturing the same patch of fault over and over at regular intervals. These repeating earthquakes act like natural strain meters, providing a measure of how quickly stress is building in the surrounding rock. By tracking the timing between repeats, scientists can infer changes in the loading rate or the frictional properties of the fault. In subduction zones, microseismicity frequently outlines the boundary between the locked portion of the fault and the deeper zone of stable sliding or slow slip. These small events can help map the depth and extent of the seismogenic zone, which is critical for assessing the potential size of future earthquakes. Microseismic monitoring is also valuable in engineered settings. Hydraulic fracturing, carbon dioxide sequestration, and underground mining can all induce microseismic activity as human actions alter the stress field. Recording and analyzing these events provides a way to assess the impact of such operations and to detect potential risks before they escalate. In some cases, induced microseismicity has revealed unknown faults capable of larger earthquakes, prompting changes in management practices. There's a quiet irony in the fact that microseismicity, though individually harmless, can illuminate the conditions that lead to the most destructive earthquakes. By studying patterns in these small events, scientists gain insight into fault behavior, stress transfer, and the evolution of rupture processes. Microseismic data have shown that faults can remain active at depths where high pressures and temperatures were once thought to preclude brittle failure, expanding our understanding of where and how earthquakes can occur. Technological advances are making it possible to detect ever smaller events. Dense seismic arrays, ocean bottom seismometers, and the use of existing infrastructure such as fiber optic cables as distributed sensors are increasing the resolution of our view into the Earth's constant low-level shaking. This expanded detection capability has revealed that even the quietest areas are rarely truly still. Rather, they are threaded with tiny adjustments as the crust accommodates the slow march of plate tectonics. One quiet mystery is whether the smallest earthquakes follow the same physical laws as the largest ones. Some evidence suggests that the scaling relationships between magnitude rupture area and slip hold down to very small sizes, implying that the same processes govern earthquakes across the full range of magnitudes. Other observations hint at differences in rupture dynamics at the smallest scales, perhaps due to variations in fault, roughness mineralogy, or the influence of fluids. Understanding these differences could help refine models of earthquake initiation. The study of microseismicity also offers a way to monitor changes in stress over time. By tracking variations in the rate, location, and depth of small earthquakes, scientists can detect patterns that may signal evolving conditions on a fault. While such signals are not yet reliable predictors of large earthquakes, they are valuable for building a more complete picture of fault system behavior. In the stillness between major ruptures, microseismicity is a reminder that the seismic cycle is always in motion. Even when no one feels the ground move, the crust is adjusting, releasing strain in countless tiny increments. These events do not reset the clock on a large earthquake, but they do shape the stress landscape in subtle ways, influencing when and where the next significant rupture might occur. From a human perspective, they are imperceptible whispers in the geological conversation, yet for those who listen closely with the right instruments, they speak volumes about the deep and constant restlessness of the Earth. Over millions of years, the accumulation of these small slips leaves its mark in the rock record just as surely as the great quakes do, though on a scale invisible without the patient work of geological excavation. Each microquake is a note in the unending composition of the planet's tectonic motion, a quiet pulse in the heartbeat of the crust. When a major earthquake strikes, its shaking is often only the beginning of change. The rupture can trigger a cascade of secondary hazards that reshape the land, disrupt ecosystems, and threaten human life long after the ground has stopped moving. These hazards arise because the sudden redistribution of stress, the deformation of the crust, and the release of seismic energy alter the stability of the landscape in ways both immediate and delayed. The quiet irony of these secondary hazards is that they can in some cases cause more destruction than the earthquake itself. Another irony is that their reach can extend far beyond the fault that ruptured, affecting areas where the shaking was relatively modest. A third is that while they're driven by the same forces that produce earthquakes, they follow their own dynamics unfolding over minutes, hours, days, or even years after the main event. Landslides are among the most common and immediate of these hazards, particularly in mountainous terrain. The shaking can loosen rock and soil, already weakened by weathering rainfall or freeze-thaw cycles, sending masses of debris rushing downslope. These landslides can bury roads, dam rivers, and destroy settlements, sometimes occurring in places far from the epicenter, if the local slopes are unstable. In the 1999 Chichi earthquake in Taiwan, thousands of landslides scarred the hillsides, their scars still visible decades later. In some cases, landslides can create temporary natural dams which later fail catastrophically, sending floods downstream. Liquefaction is another major hazard occurring in water-saturated loose sediments when shaking causes the grains to lose contact with one another, turning the ground into a fluid-like slurry. Buildings, roads, and pipelines can tilt or sink as their foundations lose support, while buried structures may float toward the surface. Liquefaction was widely observed in the 2011 Christchurch earthquake in New Zealand, where entire neighbourhoods experienced ground failure despite being several kilometres from the main fault. The quiet mystery of liquefaction lies in its variability. Two nearby sites with similar soils can behave very differently during the same earthquake, depending on subtle differences in grain size saturation and shaking intensity. Tsunamis are perhaps the most dramatic of the earthquake-triggered hazards, especially in subduction zone settings, where megathrust ruptures displace the sea floor. The uplift or subsidence of large areas of the seabed pushes enormous volumes of water outward, generating waves that can travel across ocean basins at jetliner speeds. When these waves reach shallow coastal waters, they slow down and grow in height, sometimes exceeding 30 meters. The 24 Indian Ocean tsunami triggered by the Sumatra Andaman earthquake inundated coastlines in more than a dozen countries, demonstrating the global reach of such events. Tsunamis can also result from earthquake-induced landslides, either on land that collapses into the sea or under the ocean itself. These landslide-generated tsunamis can be locally devastating with little warning time because the source is so close to shore. Another secondary hazard is ground subsidence, which can occur when large areas of land settle after an earthquake due to compaction of sediments or the collapse of subsurface cavities. In coastal areas, subsidence can permanently lower the land relative to sea level, increasing the risk of flooding and saltwater intrusion. After the 1964 Alaska earthquake, parts of the coastline dropped by more than 2 meters, allowing seawater to inundate forests and turning them into expanses of standing dead trees known as ghost forests. Fires, though less a geological hazard, are also a common consequence of major earthquakes. Ruptured gas lines, toppled stoves, and electrical failures can ignite blazes that spread quickly in the chaos, after shaking, especially if firefighting infrastructure is damaged. In the 1923 Great Kanto earthquake in Japan, fires fanned by strong winds destroyed much of Tokyo, causing more fatalities than the earthquake's direct structural collapses. Earthquakes can also alter groundwater systems, changing the flow of springs, wells, and aquifers. In some cases, shaking opens new pathways for water to travel, leading to the sudden appearance of springs or the drying up of others. Changes in pressure can release gases such as carbon dioxide or methane into the water, occasionally reaching levels that affect aquatic life. These hydrological changes can persist for years, subtly reshaping the availability of water in affected regions. River channels may shift during earthquakes either through direct fault displacement or by landslides that block or divert flow. These changes can create new floodplains, alter sediment delivery to downstream areas, and disrupt ecosystems that have adapted to stable flow patterns. In some cases, the redirection of a river can have lasting impacts on agriculture infrastructure and settlement patterns. One quiet irony is that some earthquake-triggered hazards leave behind features that become part of the landscape for generations. Landslide deposits may form fertile soils. Subsided areas may turn into wetlands rich in biodiversity. Tsunami deposits can preserve a record of the event in coastal sediments, aiding future hazard assessment. Yet these beneficial outcomes are side effects of processes that are dangerous in the short term. The interplay between primary and secondary hazards means that earthquake response and recovery efforts must account for evolving risks. A region struck by a large earthquake may face weeks or months of instability as slopes continue to fail, rivers adjust to new courses, and aftershocks shake already weakened ground. In areas prone to heavy rain or snowmelt, the risk of post-seismic landslides can be especially high, as loose debris is mobilized by water. The sequence of hazards following an earthquake can compound its impacts, stretching emergency resources thin. In the long stillness between major earthquakes, the potential for these hazards remains embedded in the landscape. Steep slopes hold rock masses in delicate balance. Coastal plains of loose sediment await the shaking that could liquefy them. Faults beneath the sea store the strain that could lift or drop the seafloor. Scientists map these hazards in advance where possible using geological surveys, remote sensing and historical records to identify areas at greatest risk. While the exact timing of the next triggering earthquake cannot be known, the locations most susceptible to secondary hazards can often be identified and monitored. There is a quiet mystery in the fact that while secondary hazards depend on earthquakes to be set in motion, they often develop their own independent course once begun. A landslide may continue to grow long after the shaking has stopped. A natural dam may fail months after it formed. A river may slowly carve a new path that becomes permanent. These processes remind us that earthquakes are not isolated events, but catalysts in a broader system of Earth surface change. From the human perspective, the earthquake is the headline, the moment when the world shifts. Yet from the planet's perspective, it is also the beginning of a chain of adjustments, some rapid, some slow, that ripple outward through the physical environment. These adjustments, whether destructive or creative, are part of the same restless dialogue between the deep forces that move the plates and the surface processes that shape the land we inhabit. In the quiet aftermath of an earthquake, the land itself may bear enduring marks of the rupture, reshaped in ways that tell the story of the event long after the shaking has faded from memory. These earthquake-induced landform changes range from subtle shifts in elevation to dramatic new features etched into the terrain. The quiet irony of such changes is that while they may arise in moments of violent motion, they become part of a landscape that appears still and permanent to later generations. Another irony is that the ground may rise in one place and sink in another during the same event, each change the direct consequence of the same fault movement. A third is that features formed in seconds can persist for thousands of years, surviving long after the fault segment that created them has fallen silent. Surface ruptures are among the most direct expressions of an earthquake, visible as fresh breaks in the land where the fault reaches the surface. In strike-slip events, these ruptures may appear as offset roads, fences or river channels, the horizontal displacement measurable to the centimetre. In thrust or normal fault earthquakes, the rupture may produce a scarp, a step in the ground, that can range from a few centimetres to several metres in height. Fresh scarps are often sharp and well-defined, but they begin to erode almost immediately, softened by rain, wind and vegetation. These scarps and offsets record the amount of slip in the earthquake, and repeated ruptures over centuries can create cumulative features such as fault scarps, hundreds of meters high, or rivers displaced far from their original course. Uplift and subsidence are also common consequences of large earthquakes. Along subduction zones, coastal areas may be raised permanently above the reach of tides, exposing new shoreline and sometimes stranding marine organisms above sea level. Elsewhere, the land may subside, lowering coastal areas into the tidal zone or beneath the water entirely. Such changes can transform harbours, wetlands and estuaries in an instant. The 1964 Alaska earthquake caused parts of the coastline to rise more than 10 meters in some places, while other areas sank by as much as 3 meters, reshaping the coastal geography of the region. River systems often respond to such vertical shifts. Uplifted areas may divert channels, while subsided areas may collect new lakes or wetlands. In some cases, a sudden change in gradient can cause a river to abandon its former path entirely, a process known as avulsion. Over time, these changes can influence sediment transport, flooding patterns, and the ecology of floodplain environments. Landslides triggered by earthquakes can leave behind their own distinctive landforms, from scarred hillsides to debris fans at the mouths of valleys. These deposits, often chaotic mixtures of rock and soil, may block streams, creating temporary lakes. When such natural dams fail, the resulting floods carve new channels and leave layers of sediment downstream, marking the event in the geological record. In high mountain regions, earthquake-induced landslides can strip entire slopes bare, altering the shape of ridgelines and peaks. Another lasting landform change can occur when earthquakes rupture the seafloor. In addition to generating tsunamis, these ruptures can create submarine scarps, uplifted ridges, or deep depressions. Mapping these features requires sonar and remotely operated vehicles, but they provide important clues to the scale and pattern of the rupture. Submarine landslides, also triggered by shaking, can remobilize vast volumes of sediment, reshaping the seafloor and potentially damaging undersea cables and infrastructure. In rift zones and volcanic regions, earthquakes may open fissures at the surface, sometimes wide enough for a person to walk through. These fissures can serve as pathways for groundwater or magma altering subsurface flow, and in volcanic settings influencing eruption dynamics. Over time, they may fill with sediment or be obscured by vegetation, but their presence in the subsurface can persist for millennia. Some earthquake-induced landform changes are revealed only through careful study. Subtle tilting of the land on the order of centimeters per kilometer can alter drainage patterns in ways not immediately obvious. Over years or decades, these small shifts can reroute streams or change the extent of wetlands. Precise geodetic measurements before and after an earthquake can detect these changes even when they are invisible to casual observation. The geological record preserves many examples of past earthquakes in the form of raised marine terraces, offset river terraces, and buried soil horizons disrupted by faulting. Paleoseismologists study these features to reconstruct the timing and magnitude of prehistoric earthquakes, digging trenches across fault scarps to examine layers of sediment displaced in past ruptures. Each displaced layer is a chapter in the long history of fault movement, and by dating these layers, scientists can estimate recurrence intervals for large events. There is quiet irony in how these preserved features serve both as warnings of future earthquakes and as reminders of the resilience of landscapes over time. Human structures and infrastructure are particularly vulnerable to earthquake-induced landform changes. Roads, railways, and pipelines that cross active faults can be offset or disrupted, sometimes by meters, requiring costly repairs and rerouting. Buildings on uplifted or subsided ground may find their foundations uneven, and coastal facilities can be rendered unusable by changes in shoreline position. In agricultural regions, altered drainage or soil composition from liquefaction and sediment deposition can transform productive fields into marsh or barren ground. In some cases, earthquake-induced changes create opportunities as well as challenges. Newly uplifted land may become suitable for development or agriculture. Altered rivers may create new fisheries. Sediment from landslides may replenish beaches or build new deltas. These benefits, however, are incidental to the underlying processes which operate without regard to human needs. The persistence of earthquake-induced landforms depends on the interplay between tectonic activity and surface processes. In arid regions, scarps and offsets can remain visible for tens of thousands of years, while in humid, rapidly eroding landscapes they may disappear in decades. This variability means that the absence of visible features does not imply the absence of past earthquakes. It may simply reflect the pace of erosion and deposition in the area. From the human perspective, these landform changes are sudden, dramatic interruptions in the stability of the world. From the planet's perspective, they are brief adjustments in an ongoing reshaping of the surface, part of the same continuum of movement that slowly builds mountains, opens oceans, and rearranges the continents. The landscape we see today is a palimpsest of these changes, each feature layered over countless others, many of which have long since been worn away. In the long stillness between ruptures, the new landforms settle into the background of daily life, their origins forgotten or unremarked, until the next earthquake writes its mark once again. Once the fault has ruptured, the shaking has subsided, and the secondary hazards have run their course, the landscape enters a phase of apparent quiet. Yet beneath this stillness, the process of strain accumulation begins again, and the long stillness between earthquakes takes hold. This interval can last years, decades, centuries, or even millennia, depending on the rate of plate motion, the size of the fault segment, and the amount of slip in the previous rupture. The quiet irony of this period is that it feels like a return to stability for those living on the surface, yet it is precisely when the conditions for the next earthquake are slowly being prepared. Another irony is that faults can remain silent for so long that their hazard fades from collective memory, only to reassert itself with a single unanticipated event. A third is that while the interseismic period appears uneventful, it is often a time of steady, measurable change for those with the tools to detect it. During this long stillness, geodetic instruments show the slow deformation of the crust as strain accumulates along locked segments. On opposite sides of a fault, the land moves in directions dictated by the overall plate motion, but the fault itself remains immobile, resisting the movement. Over years, this deformation can amount to tens of centimeters, all stored as potential slip to be released in the next rupture. These motions are imperceptible without precise instruments such as GPS stations or INSAR satellites, yet they are as steady and consistent as the ticking of a clock. In some regions, parts of the fault creep slowly during the interseismic period, relieving strain without generating large earthquakes. This creeping motion can reduce the size of future ruptures by preventing the accumulation of strain on those sections, but it can also transfer stress to locked segments, increasing their eventual slip. The interplay between creeping and locked portions of a fault is one of the quiet mysteries of fault mechanics, with significant implications for seismic hazard. The long stillness also allows surface processes to reshape the features left by the last earthquake. Fresh scarps are worn down by erosion, vegetation regrows on landslide scars, and new sediment is deposited in subsided areas. Rivers may adjust to new gradients, cutting into uplifted terraces or filling in new basins. In this way, the landscape gradually obscures the evidence of past ruptures, making geological records essential for reconstructing seismic history. Over human timescales, the absence of earthquakes can lead to a sense of security, influencing patterns of settlement, infrastructure development, and resource use. Towns and cities may expand into areas that were once recognized as hazardous, and critical facilities may be built across active fault traces. The irony is that the conditions which make a location attractive for development, flat ground, fertile soils, access to water, are often the products of tectonic processes that also carry seismic risk. The long stillness is not without its subtle movements. Small earthquakes, sometimes only detectable by sensitive instruments, occur as the crust adjusts to minor changes in stress. In subduction zones, slow slip events may shift the land by millimeters over days or weeks without generating strong shaking. Deep within the mantle, the subducting plate continues its descent, bending and deforming as it sinks, maintaining the overall motion that will eventually be expressed in another surface rupture. One quiet mystery of the interseismic period is the role of fluids in fault zones. Over decades, water and other fluids may migrate through the fractured crust, altering the frictional properties of the fault. These changes can influence whether a segment remains locked or begins to creep, and may play a role in determining the location and size of the next rupture. Because these processes occur deep underground, they are difficult to observe directly, but their effects may be visible in patterns of microseismicity or subtle changes in ground deformation, In some places, the interseismic period is punctuated by moderate earthquakes on nearby faults, redistributing stress in ways that can hasten or delay the main rupture. The sequence of events leading from long stillness to sudden rupture is complex, involving both the steady push of plate motion and the unpredictable influence of smaller disturbances. This complexity means that no two earthquake cycles are identical even on the same fault. Over the centuries of stillness, cultural and historical memory of past earthquakes can fade. Oral traditions may preserve stories of ground shaking or tsunamis, but without written records, the timing and scale of past events become uncertain. In some regions, archaeological evidence reveals the impact of earthquakes on ancient societies, showing that even in the absence of written accounts, the Earth's restlessness has shaped human history. Scientific monitoring during the interseismic period is a race against this fading memory. Networks of seismic stations, geodetic sensors, and geological surveys work to record the slow changes and hidden signals that precede the next rupture. While these records cannot predict the exact moment of failure, they can refine estimates of hazard and guide preparation. The challenge is in communicating the importance of these invisible processes to communities that may have lived without a damaging earthquake for generations. There is a quiet irony in the fact that preparation must often be strongest when the risk feels most distant. From a planetary perspective, the long stillness is simply one part of the ongoing cycle of strain accumulation and release. The plates continue to move, driven by mantle convection, and slab pull and faults continue to resist and yield in turn. The landscapes shaped by these cycles, mountains, valleys, coasts, are as much the product of the quiet intervals as of the moments of rupture. For humans, however, the stillness can be deceptive. It can foster the belief that the earth has settled into a lasting peace, when in reality it is only pausing, storing the energy that will one day be released again. The next earthquake is already taking shape in this quiet time, its magnitude and location determined by processes unfolding invisibly beneath our feet. And when the silence ends, the change will come suddenly, as it always has, marking the close of one cycle and the start of the next in the unbroken sequence of the planet's tectonic life. The land rests in its current shape, a surface settled after movement yet never truly still. Deep beneath the slow drift of plates continues without pause, their meeting places locked in quiet tension. The air above is calm, the hills hold their outlines, and the sea moves only to the rhythm of wind and tide. In this interval, the planet seems unchanging, though every grain of strain is already finding its place for what will come far beyond the measure of a single life. Mountains remain in their places, rivers follow their carved paths, and the coastlines breathe in and out with the tides. Stone holds its patterns of fracture. Sediments keep their quiet layering. Far below, heat moves upward in imperceptible currents, carrying the same forces that have shifted continents and raised peaks over deep time. The same patient processes that once bent and broke the crust continue now steady and unhurried. The silence here is not emptiness, but a pause in motion, a lengthening of stillness in which even the smallest tremor is rare. In this long quiet, the surface we see and walk upon feels certain. Its ridges and valleys seem set, its forests and fields enduring. The fault lines sleep beneath them, waiting in a time frame larger than the span of human years. No urgency presses on them. No measure of the day or season alters their pace. The next movement lies far ahead beyond the horizon of immediate thought, carried only by the slow pull of forces that will never cease, and so the surface rests its shapes in balance, for now its edges softened by wind water and the passing of days. In the quiet between changes, the earth keeps its place under a sky untroubled by what lies beneath, and the long stillness extends without end in sight.